Thank you very much. Thank you, Clément and Jaume, for the introduction. Thank you also to the organizing committee. It's a great pleasure to be included in this program. And thank you for joining this afternoon in this session. So let's get cozy, comfortable, and contemplate our energy system. Now, I'm not talking about prehistoric times. I'm talking about today, our current energy system. We are still at an age of fire. Why? Because fossil resources still represent about 85% of the world energy portfolio, and we utilize them in a completely linear economy scheme, in which we directly burn those resources to produce energy and, of course, carbon dioxide, or we try and valorize the side products of the refining of petroleum and gas to introduce chemical functionalities by oxidation chemistry in order to generate more functional groups such as alcohol, ketones, esters, amides, etc., so that we have useful products, drugs, fertilizers, plastics, etc. Of course, the problem is that we have to deal with those waste materials at the end, waste plastics, but also carbon dioxide. And I'm therefore advocating for a paradigm change, and we need to develop more reduction chemistry. This means trying and develop efficient procedures to reduce back carbon-oxygen bonds and reform CC and CH bonds. So in my research group at CA, we are developing different research lines. The first one is to look at new catalytic systems to understand and to try and reduce carbon-oxygen bonds. Of course, trying to develop recyclable and energy-efficient chemical reductants, and to utilize those methodologies for the conversion of oxidized wastes, such as CO2 chemistry, CO chemistry, waste plastics, and wood lignin. So today, what I'm going to do is pick a selection of research topics on CO2 and CO chemistry, as well as the depolymerization of waste polyesters and polycarbonates. So let's dive first into CO2 chemistry. I would say that today, most of us, we try to develop and to utilize hydrogen as a power molecule, meaning to utilize H2 coming from the electroreduction of water using low-carbon electricity, and to utilize hydrogenation technologies to convert CO2 in order to form simple molecules like methanol, methane. Those are the most frequent molecules, and trying to develop some tandem chemistry to access olefins and hydrocarbons. That's not what nature is doing. Nature is much more sophisticated. So what is nature doing? And can we get some inspiration into CO2 conversion by nature? So first, nature is not utilizing H2, and most of the time it's utilizing a chemical reductant, such as NADH or NADPH, so such a reductant, instead of H2 or electricity and protons to reduce carbon dioxide. And second, nature is able to efficiently convert, reduce, but also couple together CO2 molecules, for instance, for the production of acetic acid. In acetic acid, this is a fascinating molecule. Why? Because one carbon atom is fully reduced to the methyl stage, while a second carbon atom coming from carbon dioxide is coupled to that methyl group, but reduced only by one electron. So how does nature cope with the fact that it needs to handle very different oxidation states and being able to couple carbon-carbon bonds coming from carbon dioxide? So in acetogenesis, the Wood-Jandal pathway follows two branches. The first one is the methyl branch, in which CO2 is first reduced to formic acid. And then formic acid is captured by a cofactor, which is a tetrahydrofolate, a very simple organic molecule, which will trap the carbon atom and form a formamide intermediate. And then this formamide will undergo a sequence of different reduction steps, so that at the end, the carbon atom coming from carbon dioxide in the formamide ends up in the form of a methyl group. And second, we need to create at some point a carbon-carbon bond to generate acetic acid. And it's a completely different enzymatic sequence that is involved. First, to reduce CO2 to CO, and then a cobalamin is going to be able to take the methyl group coming from the methylated tetrahydrofolate and to couple it with carbon monoxide so that acetic acid can be generated. So what I would suggest is that we need to reinvestigate carbonylation chemistry and try and utilize CO as a new power molecule, or an old monkey, and utilize CO as a power molecule, trying to couple together the reduction of CO2 to CO, and therefore the downstream utilization of CO in carbonylation chemistry. In fact, carbon monoxide is already a very useful molecule and platform chemical in the chemical industry. It's used as a scale of about 55 megatons every year for the production of methanol, of course, but also in hydroformylation processes, the Cativa and Monsanto processes to generate aldehydes, alcohols, acetic acid, and so on. Yet, today, CO is still completely derived from fossil feedstocks, either from gas or from coal. And in our research lines, what we're trying to develop is to unveil new atom-efficient catalytic reactions that are able to utilize CO. For instance, I'm going to present some reactions where CO is directly inserted into sigma bonds. And secondly, what we try to do is to unlock the production of CO from renewable sources of carbon, for instance, from the electroreduction of CO2, and then to use in a downstream process such carbon monoxide into a carbonylation process. So the first research question that we have is, can we develop efficient catalytic reactions where we are going to utilize the fact that CO has a carbonic character to try and exploit this carbene character so that we can insert directly CO into a sigma bond, for instance, an AB bond. This will allow the production of carbonyl products with a pure and ideal atom economy. It's already a reaction that exists at scale, because the Monsanto and the Cativa processes for the production of acetic acid are actually able to cleave the carbon-oxygen bonds of methanol to insert CO so that acetic acid can be produced with an ideal atom economy. Similarly, the carbonylation of epoxides, which is a more recent reaction, can give you an easy access to lactone monomers directly by carbonylation of epoxides. So our target for today is the following. Can we cleave a very strong and even a stronger bond compared to a carbon-oxygen bond, cleave the carbon-nitrogen bonds of an amine, and insert CO in between the nitrogen and the carbon atom so that we can generate an amide derivative. So there are a couple of reactions, I would say isolated reactions, which are able to perform the carbonylation of nitrogen-carbon bonds in the presence of activated substrates. For instance, when you are in the presence of a benzylamine or in the presence of a strained aziridine. So how can we develop such a reaction? Our idea was to go back to the Monsanto process because it's well known and the mechanism has been very thoroughly studied. And in the Monsanto process, you use two components in your catalytic system. The first one is a low-valent rhodium or iridium metal catalyst. And the second one is an acid, for instance, iodic acid. And the acid is actually doing most of the job because the acid is responsible for cleaving the very strong carbon-oxygen bonds in methanol. Why? Because HI is involved in an equilibrium with methanol to generate methyl iodide. And what the metal catalyst is able to do is actually to trap by a nucleophilic substitution reaction this methyl iodide to generate a metal methyl cation that undergoes a carbonylation of the carbon-metal bond to generate an acylium intermediate. This acylium intermediate is captured by the iodide anion, which acts as a nucleophile, and after hydrolysis, you generate acetic acid and regenerate your HI co-catalyst. So the question is, can we transpose the Monsanto process to amines? So can we replace methanol, for instance, using a methylamine, and try and promote the carbonylation of the methyl nitrogen bond? In principle, we could write the very same mechanism for such a transformation. But the main problem is going to be this equilibrium here, because the amine is nucleophilic. Of course, it's going to trap the methyl iodide intermediate, which is key in the catalytic process to generate a very stable ammonium salt. So in principle, what we need, of course, to increase the reaction temperature so that we favor this equilibrium. But second, we need a metal catalyst that is extremely nucleophilic so that it's going to be able to capture very small concentrations of methyl iodide. The idea is therefore to go back when you have such a difficult and challenge is to go back to the previous literature. So we went back 50 years ago. Because 50 years ago, our colleagues in organometallic chemistry, they developed highly nucleophilic, low-valent iron carbonyl complexes. And for instance, if you take this iron 0, FIP anion, which is very well known in the literature, it's about 8 orders of magnitude more nucleophilic than the archetypical cobalt tetracarbonyl anion. And in fact, if we utilize this FIP anion based on iron 0, we can promote the catalytic carbonylation of dimethyl aniline at 200 degrees using only 8 bars of carbon monoxide. The FIP anion is not the only active low-valent iron complex in this catalytic reaction. We can also use the Coleman reagent, which is formerly an iron -2 catalytic system, so it's an iron tetracarbonyl dianion. It has a very similar reactivity. Interestingly, when we increase the reaction pressure from 8 bars of carbon monoxide to 55 bars, we can even promote a quantitative transformation of the amine derivative to the corresponding amide. So this means that from a mechanistic perspective, transposing the Monsanto process to amine chemistry can indeed promote the carbonylation of amines to amides, meaning that we have trapping of methyl iodide intermediate to generate an iron methyl intermediate, which is able to undergo a carbonylation step so that we can create an acyl intermediate, which is in turn trapped by the amine substrate, to generate the amide product. Interestingly, the fact that increasing the pressure has a positive influence on the catalysis means that what is actually rate determining as a step is the carbonylation of the iron methyl bonds. And it is known that Lewis acids can promote such a transformation by coordinating to a CO ligand. So to lower the reaction pressure and to increase the scope of the reaction, what we did was to utilize a very specific Lewis acid, which is neodymium triflate, which is still reactive in the presence of amides and amines and can selectively activate the carbonyl ligands on iron to unlock the carbonylation of different substrates. Of course, the reaction is still limited. You can see, for instance, that if you take completely aliphatic amines, because those are more basic and more nucleophilic compared to the aromatic amines, the ammonium salt is still extremely stabilized and the conversion drops. The next challenge is, of course, to try and couple CO production from CO2 electroreduction with a downstream carbonylation process. So we teamed up with a group of Marc Foncave at the Collège de France, trying to explore a very basic idea. Can we couple the electrolysis of CO2 to CO with a downstream carbonylation reaction, for instance, the well-known carbonylation of an epoxide to a lactone? So in the coupling, first we need an electroreduction process that is able to produce a lot of carbon monoxide so that we can utilize this carbon monoxide in a high-pressure carbonylation step. So the group of Marc Foncave developed very nice cathodic materials for the reduction and the selective reduction of CO2 to CO. For instance, zinc, which is doped with silver, can undergo and can promote the reduction of carbon dioxide to carbon monoxide with a very high Faraday efficiency of about 80%. This means that if you take a pure gas of CO2, for instance, 8 bars of CO2, at the end, after electrolysis, we are able to generate about 8.5 bars of a mixture of gases. Of course, not all the CO2 is converted, so that at the end, what we get is a mixture of CO2 with about 1/3 of carbon monoxide and some dihydrogen, which results from the reduction of the protons. For the carbonylation step, what we are looking at is the carbonylation of an epoxide with carbon monoxide to generate a lactone. So the catalytic system that we used was very well known in the literature. It has been developed nearly 20 years ago by the group of Geoff Coates in the US, who showed that you can use this cobalt tetracarbonyl anion in the presence of a chromium-based Lewis acid to insert CO into an epoxide and generate the corresponding here beta-butyrolactone. You can have some side products if you have a double insertion of the carbon monoxide, and of course some oligomers, because you can polymerize both the starting material and the lactone intermediates. So we visited this chemistry taking this well-known Coates catalysts, and indeed, if you expose the epoxide in the presence of pure carbon monoxide, after 2 hours under 5 bars of carbon monoxide, you get an expected yield of about 80% of the beta-butyrolactone. But now we need to take into account the fact that, well, actually, it's not pure CO that's going to come out of the electrocatalytic device. It's a mixture of CO with some carbon dioxide, a lot of carbon dioxide actually, and some hydrogen. So we need to test whether such a catalytic system is robust enough to cope with the presence of those potential pollutants. In particular, when you mix together an epoxide with carbon dioxide and a catalytic system, you might expect the formation of carbonates. So that's what we did, and we did emulate different gas mixtures to emulate what was coming out of the electrocatalytic device. So adding some hydrogen, some CO2, and mixtures of CO2 and hydrogens. And it turns out that this particular carbonylation catalyst is actually quite robust, and we were able to maintain the same productivity and the same selectivity for the production of the beta-butyrolactone, regardless of the nature of the gas phase. So now it looks very promising, and we should be able to couple the two processes together, just taking out the gas phase coming out of the electrolysis to perform the carbonylation reaction. But when we just tried this very simple approach, of course, we had no productivity at all. And the reason why is simply because under electrolysis conditions, of course, you generate a mixture of CO and H2, but you also generate some traces of dioxygen coming from the anodic oxidation of water to dioxygen, and some water traces. And the carbonylation catalyst is completely intolerant to dioxygen and water. So we had to purify the gas phase before the carbonylation step. So it's mostly of an engineering problem where we had to remove water by dehydration to remove dioxygen using copper on charcoal so that we could completely clean the gas phase in order to unlock the carbonylation. And in this case, we were able to restore completely the catalytic activity of the catalytic system and to produce the lactone, but also the anhydride in 80% yield and 9% yield respectively, directly from CO2 that is first converted to CO and then used in the carbonylation process. So the productivity is very similar to using pure CO. Nonetheless, I would say that the interesting metrics is not really what is the yield in the lactone or the yield in the anhydride. The interesting yield is how much CO2 did we actually convert. And when we calculated the yields, although this is the first process to demonstrate the coupling of CO production from the electroreduction of CO2 with a downstream carbonylation process, the yield is extremely low, below 2%. And I think this teaches us many lessons of what we should do and what we need to do as a community for the next steps if we really want to boost the conversion of CO2, if we want at some point to develop sustainable processes able to convert CO2 and especially to utilize CO2 in the production of chemicals. First, regarding the electrolysis step, we need better CO2 conversions. It's not okay to spend a lot of energy and a lot of money capturing CO2 from the air or from a point source if we are only converting a small fraction of the CO2, especially if we produce gas mixtures, because it means that at the end, to be able to recover the CO2, to purify it, we're gonna need to spend the energy needed for the separation of CO2 from CO, from H2, from water, etc. Second, we need to develop devices which are able to perform high-pressure electrolysis of carbon dioxide to CO, especially because most of the carbonylation reactions, they are performed under elevated pressure of carbon monoxide. And second, it's more of an engineering problem, but engineering and chemical engineering is really key when it comes to CO2 conversion. We need to suppress any pollution coming from dioxygen in the output gas phase. When it comes to carbonylation chemistry, I truly believe that we need to revisit thermocatalysis and especially carbonylation chemistry because we need to develop more robust catalysts which are able to cope with the presence of pollutants that we never considered in the past, especially the presence of carbon dioxide, the presence of water, the presence of dihydrogen, etc. And of course, we also need low-pressure carbonylation catalysts so that the overall conversion when it comes to the conversion of CO is much higher. So many research lines that we need to develop in the future. Another quite challenging topic, of course, is the depolymerization and the recycling of waste plastics. So if we zoom at the European level, today we are producing about 30 million tons of waste plastics every year, which are collected, efficiently collected, but still the end of life is not ideal because 23% are deposited in landfills, 42% are incinerated, and only 35% is recycled. And when we are saying recycling, it's not an ideal recycling process because it's mostly a mechanical recycling process which degrades the polymer matrices, which degrades the properties and the functionalities of those polymers so that at the end, we still need to incinerate and to deposit them. The ideal process of recycling, which would be a complete depolymerization that we could go back to the monomers, so a chemical recycling of those plastics. They only represent 1% of the waste plastics that we deal with. So in an ideal depolymerization process, what we want to be able to achieve is to cut down the polymer chain to recover the monomers so that we don't have to degrade the properties and we can regenerate pure virgin materials. So many approaches for depolymerization exist to go back to the monomers: hydrolysis, alcoholysis, aminolysis, or reduction chemistry. And reduction chemistry is mostly emerging since almost 10 years, where reduction chemistry is utilized to cleave carbon-oxygen bonds, for instance, in polyethers, polyesters, and polycarbonates, to go back either to monomers or to value-added products like alcohols and alkanes. So the field was developed first by the group of Robertson, about 10 years ago, using dihydrogen as a hydride source and ruthenium catalysts, so that the hydrogenation of ester functionalities or carbonate functionalities in polyesters and polycarbonates could help cleave the polymer chain and go back to either alcohols or even the monomers. At the same time, we explored the utilization of hydrosilanes and hydroboranes, so silicone or boron-based reductants, which are already polarized and feature a hydridic character so that you can efficiently cleave esters and carbonates using very simple catalysts, such as this borane-Lewis acid, which is able to reduce polyesters and polycarbonates even to alkanes at room temperature. More recently, we showed that we can even utilize hydroboranes, so reductants featuring a boron-hydrogen bond, using simple lanthanum, basic lanthanum complexes to depolymerize polyesters. But again, some big challenges. The idea at the end is not to convert pure, commercially available polymers, but to really deal with the true materials, the true waste, which is soiled, which actually we don't want to sort, wastes which contain additives, such as adjuvants, such as pigments, etc. So the question for catalysis behind is not just reactivity towards reactive groups, but also selectivity. So how can we use catalyst design to improve the selectivity and ideally directly to depolymerize contaminated plastics or even to depolymerize mixtures of plastics without the need for sorting them beforehand. So in reduction chemistry, you can reduce many functionalities from aldehydes, ketones, esters, amides, and carbonates. And you can see on this order of reactivity that the esters are easier to reduce compared to the amides, and the most difficult groups to reduce are the carbonates because of the delocalization of the lone pairs on the oxygen atoms in the pi system of the carbonyl group. So what can we do about the selective reduction of those carbonyl groups? I'm just going to pick something that looks unrelated to the depolymerization of plastics, but that we can use at the end for depolymerization and selective depolymerization of polyesters and polycarbonates. A very well-known challenge in reduction chemistry is the possibility to reduce an amide. And when you reduce an amide, the first product that you are going to form is an imide. And this imide, or imine, if you prefer, it is actually more reactive compared to the amides because it has the same reactivity in reduction chemistry that an aldehyde. And usually, if you are able to promote the reduction of an amide, you will not stop at the imine stage, and you will directly over-reduce it to the amine. So developing a catalytic system that is able to stop at the imine is extremely challenging. So how can we approach that? Again, we love old textbook chemistry. And in 1993, the group of Bruce Ganem in the US showed that you can use the Schwarz reagent, which is a zirconocene hydrochloride complex, to reduce under stoichiometric condition an amide. First, you coordinate the amide to the zirconium catalyst by protonolysis, and a second zirconium hydride complex is going to cleave the carbon-oxygen bond and transfer a hydride from zirconium to carbon so that you can generate the imine. And there it stops. Under stoichiometric conditions, you have consumed all your zirconium hydrides, and you form the imine and a zirconium oxide side products. The question is, can we find a suitable reductant that will be able to convert back the zirconium oxide into the reactive zirconium hydride without reducing the corresponding imine. So what we found out is that if you use a hydrosilane, in this present case, an alkoxysilane, what you can do is unlock the selective reduction of the amide to the imine, and the catalytic system stops at the imine. It's not able to trap on the imine to convert it back to the amine. I don't think you are an organic chemistry community. I'm not going to discuss the scope, but there are some key and interesting elements there. You would notice that in this particular substrate here, we have an ester functionality. Here we have a cyano group, a nitro group there. And although we have all those reactive groups, which are easily reduced in the presence of a hydrosilane, in this present case, we selectively reduce the amide to the imine without touching those oxidizing groups. And in particular here, although the ester is easier to reduce compared to the amide, it is still the amide that is reduced first to the imine, and neither the imine nor the ester are reduced in the presence of the Schwarz catalyst. So let's look at the mechanism, try and identify where is really kicking in the selectivity in this catalytic reaction. So from a mechanistic point of view, the zirconium hydride first coordinates by protonolysis to the amide, dehydrogenating this NH bond in the amide to generate an intermediate. In this intermediate, the substrate is activated by coordination to zirconium, so that a second equivalent of the metal complex featuring a zirconium hydride bond is able to reduce this amide, transferring the hydride from zirconium to carbon, where the oxygen is going to be sucked by the two zirconium atoms to form a zirconium oxide. The side product is actually the desired product. It's the imine that we are looking for. And the final step to close the catalytic cycle is, of course, to be able to regenerate this zirconium hydride. And thankfully, the hydrosilane derivative that we are utilizing is just hydraulic enough to transfer a hydride back to zirconium without reducing the imine. That step here is somewhat uphill, but what is actually the most exothermic step is the deoxygenative reduction of the amide to the imine. So actually, the selection of the substrate is ensured by the coordination of the amide to zirconium. And therefore, the best ligand for zirconium is actually the first which is reduced. So because we are actually able to reduce amide with zirconium hydrides, in principle, we should be able to reduce esters as well, because they are easier to reduce compared to amides. And in fact, if we take polycaprolactone as a model substrate of a polyester, in the presence of that zirconium hydride catalyst with a hydrosilane reductant under stoichiometric conditions, we can completely depolymerize polycaprolactone to generate the silylated alcohol. The reaction works also for polylactic acid. And what's interesting in this reaction is the fact that the Schwarz catalyst is able to reduce both polylactic acid coming from 3D printing wires, which are tinted in blue or in white, although in white you have a very large charge of about 20% of titanium dioxide. Still in the presence of such an additive, the zirconium hydride catalyst is able to maintain a very good catalytic activity. And finally, for polyethylene terephthalate, the zirconium hydride is still able to depolymerize polyethylene terephthalate, even coming from a colored bottle of Perrier for the French people, the French community. You can reduce all the carbon-oxygen bonds in the ester functionalities to generate the two silylated alcohols. So those products are not the monomers. It's mostly an upcycling because you form value-added products from PET. In this particular case, what we isolate are the reduced products coming from the monomers. What about carbonates now? And this will be my last example for today. The carbonates are more difficult to cleave compared to the amides. And even though they are more difficult to cleave, the Schwarz catalyst, again, is able to reduce, under catalytic conditions, carbonates and polycarbonates. For instance, if you take the polycarbonates coming from bisphenol A, either commercial samples or waste samples coming from compact discs, you can completely depolymerize the polycarbonates of bisphenol A and to recover after hydrolysis the monomer in a pure form. In terms of selectivity now, a carbonate is a much better ligand for zirconium compared to an ester. And in fact, if we take a mixture of the polycarbonate with the PET, so the polyester, what we observe is that PET is completely left untouched by the zirconium catalyst, and only the polycarbonate is deconstructed and reduced by the Schwarz catalyst because it's actually a better ligand for zirconium, so it will first coordinate to zirconium so that it can get reduced before PET is finally converted if we have a very large excess of the reductant and prolonged reaction times. So that's the end of my presentation today. Before we can discuss, if you have any question, I would like to thank the students and postdocs who did this job. So the carbonylation chemistry was performed by 2 PhD students, Taufik Nasrallah, who is now the CEO of Fabrics, and Louis Ponsard. And the depolymerization of polyesters and polycarbonates was performed by 2 postdocs, Liam Donnelly and Cyril Tellier, and 2 PhD and master students, Mariko Bilarski and Frederike van der Haar. And thank you very much for your attention.